Hi everyone, we're going to start talking about section 8.2 in this video. In section 8.1 we most recently talked about the difference between electrolyte and non-electrolyte solutions. You can see that comes up in 8.2 as well. And we talked about solubility. The first two bullets in our objectives for this unit are about electrolytic versus non-electrolytic solutions and determining whether an ionic compound is soluble or insoluble using solubility rules. So let me first remind you a little bit about how salt dissolves in water. Salt is, of course, an electrolyte. In other words, it's going to form an electrolytic solution when it's dissolved in water, and that's because it dissociates into ions. And I've got an animation here which will kind of demonstrate what happens when you put salt. Here comes a salt crystal, or what we would call a formula unit of salt. Sodium chloride. When it is dissolved in water, it dissociates into sodium ions and chloride ions. And that's because of the ion-dipole interactions between sodium ions and water's dipoles and chloride ions and water's dipoles, like I explained in the earlier video. This is what we call dissociation. When a soluble ionic compound dissolves, the ions break apart like this. Now, let's look at a different situation. We'll look at an insoluble ionic compound like silver chloride. When you put silver chloride in water, it does not dissociate. It's an insoluble compound. What happens? It simply does not break apart into ions. When it hits the water, the ion-dipole interactions are not strong enough to disrupt that ionic bond, and so the silver chloride will simply sit at the bottom of the beaker as solid, undissolved silver chloride. That's the difference between a soluble and an insoluble ionic compound. Some compounds are soluble in water, and that means we can make solutions that are at least 0.1 molar. Examples are sodium chloride, silver nitrate, ammonium hydroxide. These are all highly soluble in water, and that's because the ion-dipole interactions between these ions and water molecules are strong enough to disrupt the ionic bond. Some compounds are insoluble in water, meaning we can't even make solutions that are more than 0.001 molar. Examples would be silver chloride, calcium carbonate, which is chalk, or calcium hydroxide. In cases where an ionic compound is insoluble in water, the ionic bond is too strong to be disrupted by the ion-dipole interactions between its ions and water. Now you'll notice there's an intermediate range between the two molarities that I referenced there, and some compounds would be classified as just moderately soluble in water. Those borderline or intermediate cases we're going to ignore in this course, and we're just going to either classify compounds as being soluble or being insoluble. So let's take a look at the rules, the solubility rules, that we're going to use to determine whether a compound is classified as soluble or insoluble. This is also going to be posted in Classroom, and the way these rules should be used is to read through them in order to determine whether the compound you're considering is soluble or insoluble. The top rule says all salts containing nitrate or acetate anions are soluble. If you have a salt with one of those two anions present, then read no further, it's a soluble compound. The second rule says any salt containing an alkali metal cation, that's a group 1 cation like sodium or lithium and so on, or the ammonium cation, those are soluble compounds, no exceptions. Rule number 3 says that halogen salts, those are, in other words, halides, chloride, bromide, iodide, and so on, those are highly soluble. There are 3 important exceptions: silver halide, mercury 1 halide, and lead 2 halides. In other words, something like silver chloride or silver bromide and so on, those would be insoluble. Sulfate compounds, rule number 4, are soluble, but there are also some important exceptions there. Calcium sulfate, barium sulfate, lead 2 sulfate, and mercury 1 sulfate are all insoluble compounds. Rule number 5 says most hydroxides are insoluble. There's an asterisk there because, of course, sodium hydroxide would be an exception according to rule number 2. And sulfides, carbonates, chromates, phosphates, and oxides, those are all insoluble compounds. And the asterisk, again, is just reminding you that if a higher ranked rule has already determined that the compound is soluble, then of course those lower ranked rules won't count. So a compound like sodium sulfide is soluble. Read the rules in order. We're going to do some practice with an assignment which is a bracket of ions. And I'm going to go through one sample assignment before I give you the assignment which I'll ask you to complete on your own. Here's the example assignment that I'm going to walk through. The rules are in the bottom right-hand corner. It says in the first round we add charges. In the second round we write the formula. And then I'll show you how the semis and finals and the winner is determined. In the first round we're going to add charges. Barium is, for instance, going to be a +2 cation because it's a group 2 alkaline earth metal. The carbonate anion is what's referenced here. That's a -2 anion. And again, this is not carbon trioxide, this is an ion. Magnesium is a group 2 element, so it's going to be 2+, and sulfate's going to be a 2- anion. Remember, this is not sulfur tetraoxide, these are ions. So how am I going to make a compound here, for instance with magnesium and sulfate? The same way I did with barium and carbonate. These are both +2 and -2 anions, and so that's going to be a simple 1-to-1 ratio. But lithium is a +1 cation and phosphate is -3. And when I want to make a neutral compound from lithium and phosphate, I'm going to need to use 3 lithium cations for every 1 phosphate anion. So a good review of the logic behind how ionic compounds formulas are determined by the preferred charges of the ions involved. The Roman numeral 1 on copper here means that we're talking about a copper 1 ion, and sulfide, of course, is always -2, just like any other group 16 element. So the formula we're going to get here is Cu2S. 2 copper cations, copper 1 cations, and 1 sulfide anion. Let's go ahead and look at the second half of the bracket. I'm going to add charges here to each of these. Zinc, you might remember, is one of those transition metals which always has a preferred charge, a +2, and hydroxide is a -1 anion. Calcium is always a +2 cation, chloride is -1. This is a lead 2 ion, this is the acetate anion. This Roman numeral is telling me we're talking about iron 2, and the chromate anion is -2. So let's go ahead and make these compounds. Notice here, I'll need to use brackets. Here, I'm going to again have 2 of the anions for every 1 cation, since calcium is +2 and chloride is -1. In this case, I've got rather a complicated formula because I'm going to need 2 of those acetate anions, so make sure to put the subscript outside of the parentheses. 2 acetate anions at -1 each cancels out the +2 charge of lead. And in this case, we've got iron chromate, which is a +1 cation and a -1 anion. Let's talk about the rest of the rules. Rule number 3 says that the semifinals are going to be determined by whichever is the soluble compound. So now we're going to start using the solubility rules. You'll notice if I read through the solubility rules, I can determine the solubility of either of these compounds. One rule says that carbonates are insoluble. Now, I'd have to read through rules 1 through 5 before I found a rule that applied to barium carbonate, because none of the first 5 rules apply. But when I get to the last rule, it says carbonates are insoluble. So that one's not going to advance to the semifinals. If I start reading through the rules from the top to consider which ones apply to magnesium sulfate, it's not until I get to rule number 4 that I see it mentions that sulfates are soluble except for those of calcium, barium, and lead. Well, this is not one of those exceptions. Therefore, magnesium sulfate is a soluble compound, and mixed with water it would be an aqueous solution. So the soluble compound advances here. Which one's soluble here, lithium phosphate or copper 2 sulfide? The very second rule, the first rule doesn't apply to lithium phosphate, but the second rule does. All alkali metal compounds are soluble, and so immediately I know this one is soluble. And just to double check, I could look at all of the rules that apply here, and again, it's not until I get to the last rule which says this, being a sulfide, is an insoluble compound. So good, only one of those two can advance. Again, when I apply the rules here, I'm going to read through several rules before I find a rule about hydroxide salts being insoluble, but the very second rule tells me that calcium chloride, since this is a halide, is going to be a soluble compound. Here, we have lead acetate and iron chromate. Acetates, of course, are always soluble compounds. And so that one's going to advance, and we're ready for the next round. Let's look at the rules one more time, and the finals, you can see, are going to be the soluble product of a chemical reaction. Now, this is a little bit more complicated in that we're asked to consider the product of a chemical reaction. In other words, consider a chemical reaction that occurs between this species and this species. That would be a double displacement reaction. We would end up with magnesium phosphate and lithium sulfate. So which of those two is going to be the soluble product of that chemical reaction? Magnesium phosphate would be insoluble because phosphates are insoluble. But lithium sulfate, since it's a lithium compound, which is an alkali metal, would be a soluble compound. So we'll do the same trick for the last one here. We're looking for the soluble product of a chemical reaction. This reaction would produce calcium acetate and lead 2 chloride. Well, calcium acetate is soluble because all acetates are soluble. Lead 2 chloride, remember, is one of those exceptions to rule number 2. So it's calcium acetate which is going to advance here. Let's see. Calcium is a +2 cation. Acetate is a -1 anion, so I'm going to need that subscript again like I did previously. The final step is to determine the winner, which is going to be the insoluble product of a chemical reaction. So let's consider a chemical reaction here between lithium sulfate and calcium acetate. That would give me lithium acetate. Well, that's certainly a soluble compound because it's got acetate and lithium. An alkali metal and an acetate, both of those are one of those first two rules which take precedent over all others. That's going to be a highly soluble compound. Calcium sulfate, well, I thought all sulfates were soluble according to rule number 4. Remember, sulfates are soluble except for those of calcium, barium, lead. So those exceptions need to be considered. The winner of this tournament here is this insoluble compound. As a reminder, when a compound is insoluble, then in water the state symbol would be an S for solid, not S for soluble. If a compound is soluble, then the state symbol we'd give in a reaction is AQ. In other words, it exists in aqueous solution as dissociated ions. So we're going to look at another one of these as an assignment which has the same kinds of rules but different ions and different compounds, but you can look back at this video to remember how those rules were applied.